Hello and welcome back to ST118 Statistics and Applications, Session 4, Part 2. In this session, we want to discuss everything about confidence interval. Confidence interval, right? And the two kinds of problems regarding confidence intervals, right? Um, One is to form interval, the other one is to estimate sample size. We'll come to that. Okay, so to start, let's recall that the sampling distribution of sample mean is derived from a sample size of n measurements. So we, of course, first remember that our goal, what's the goal? Our goal is we have a population of measurements of numbers x, right? That's our parent population, parent distribution. I call it parent because we're soon going to give birth to uh, the child distribution, which is the x bar, right? Okay, okay. So this is the nature. This exists in reality, and it can be any distribution. Okay, so all right, so it can be any distribution, any shape, but right, so long as there is this presence of mu, which is what we are trying to determine. We're trying to estimate that, and sigma, the population standard deviation, and the y-axis is the relative frequency, for example, or probability. And so this is our whole entirety, what we call distribution, right? So our population of measurements of numbers occurring with these relative frequencies of percentages. And our goal, remember our goal is to estimate or determine mu with a trade-off, right? Because the only way to determine mu with infinite precision and accuracy is to measure each and every entity in the population. For example, Singapore working population in 2024. Then find their income, and then we can determine the population mean income of Singaporeans in 2024. So we are saying that we don't have the time, energy, budget, and manpower to measure, interview, right, to gather every single income. And so we make do with a smaller sample set. And so we discussed that a lot about sampling and the resulting sampling distribution of sample means, right? So we said that X itself, right, X itself is not touchable, the untouchables. So X mu is a summary of X, right? Yeah, the central location of X that we want to know, but we are unable to measure directly. So we trade off and we make n measurements. We make n measurements. Whether it is interview or using sensors or instruments, right, we make n measurements, n quantities. And that would result in x bar of subscript n. From here on, I will not write down the subscript anymore because we are going to, in real life, that's what we do. We make n measurements and then take the average, right, and use that point to put it on the x bar x-axis. So it's one of the point on the x bar. But we talked about it in the previous video that we're going to imagine. The theory says we repeat this n sampling infinite number of times, take the average, put a dot here, throw it back, right? Then take n random measurements, take the average, put a dot here, and keep growing the distribution until we will get, when n is large enough by central limit theorem, we will get a nice bell curve whose mean, I should correct myself here. So this is our mu. because I accidentally drew it off center a little bit. So put it back and make sure they roughly at least align. I'm not trying to be pinpoint accurate here, but certain alignment, right, is known and is to be observed, right? So it is intentional that we have this alignment of the mu. So we know from theory that the mu of capital X, remember capital letter is a random variable, and that represents the entire picture, the entire entity, right? Set of entities, set of measurements, set of numbers. Population mean of capital X, right, is in theory the same as the population mean of X bar. So we denote by mu of capital X bar. So, and this is the exact equivalence, right? Exact case for all distribution, for all parent distributions, capital X. So here we also know that the population standard deviation of X bar, from theory we learn that it is sigma over square root n. Of course, it is denoted as sigma of X bar, but yeah, so unless we need to talk something about sigma of X bar itself, we both textbooks and many statistical discussions will just simply draw it as sigma over square root n to emphasize the link back to the parent parameter here. And similarly, this mu x bar is also often just written directly as mu without the the subscript x bar here, because from theory we know mu x bar is equal to mu all the time for any kind of shape, for any kind of value of mu. So that was our previous lesson, and also we apply central limit theorem so that zigzag curves, any parent distribution, any shape with large enough n sample size will result in a smooth normal curve. So this is all recollection from previous videos. So if you haven't seen those discussions, it's a good idea, right, to catch up on that video to understand what is the true essence, the spirit behind, right, if I may just put it that way, why we so-called trust so much, why we believe so much, why we put all our calculations and formulas and derivations so much on the sampling distribution of sample mean itself, right? So X bar. So this is the, just to put it back in the same color, sampling distribution of sample mean of size n. But n in these discussions are often clear because n doesn't change. And in real life, when you plan for a project measurement for n samples, that almost always is determined upfront, right? So that you can obtain the budget, summon the necessary manpower, equipment, right, instruments and all that, then plan out the timeline and so on. So it is often not an afterthought. It is also not changed midway unless something happens. Usually reduce some more rather than increase some more. So n doesn't change. And so once it is fixed, the sampling distribution of sample mean is fixed. We won't have a lot of different X bar 1, X bar 2, X bar 3. In the previous video, we have to talk about the meanings of all these variations, varied sizes in sample size. So we want to denote the differences. But other than that, in practice, we deal with one sampling distribution of sample mean almost always. Okay, so now comes to the confidence interval. So what's so special about confidence interval? First of all, the goal is to estimate mu, right? So it's one instrument to estimate mu, and to do that, any instrument, any statistical theory and tool must start with sampling. So we did all that, right? So once we capture all the sampled values, we need to just construct this. So this gives us two numbers, X bar minus this term, and x bar plus this term. This term is called the error or margin of error or tolerance. It's got a few different terms and names referencing this value. All right, let me see what else. Tolerance, and yes, it's also usually in textbooks half width. So half width. In practice, it's usually called error, margin of error, tolerance, plus minus. I'm sure you have heard of that. What's your time of arrival? Your estimated time of arrival, your ETA, right? ETA is 3 p.m. plus minus 5 minutes. I could be early by 5 minutes. I could be late by 5 minutes. So is that a nice, accurate, right? A very responsible reply, because I do know I won't be exactly on the dot 3 p.m., but plus minus 3 p.m. And I give you, plus 3 p.m. plus minus 5 minutes. So I give you an error tolerance of 5 minutes, and that's referring to this term. Okay. So the 5 minutes is nice because it's not a big number. What if I say my ETA, time of arrival, is 3 p.m. plus minus 1 hour, which means I could be as early as 2 p.m. or as late as 4 p.m., right? And that is bad because, if you're there at the airport to receive a guest, it's going to waste as much as 2 hours, because you, as a sort of a host receiving the guest, you don't want to be late. So you reach there at 2 p.m., but the plane arrives at 4 p.m., which is not wrong because it's within the tolerance, right? So that kind of error bound, right? I'll call it error bound because it's bounding. It's the so-called maximum in that sense, right? Is too wide, too loose for practical planning purposes. So we want this error term. If you are the one giving this error bound, you want to give a quality error bound by making it as small as possible, isn't it? Yeah. But making it as small as possible means either your t is very small, yeah, because you make it small, or your s is very small. That means the point estimate, your s is small only because sigma, which we don't know the exact value, only because sigma is itself born with a small value. That's why no matter how you sample, the sample standard deviation ends up to be small, right? So then that depends on luck. What if my sigma is naturally large, right? So the only way that's within your control is n, sample size itself. So no matter what is t, what is s, you can make this entire term small by having a large n, right? Very large n. So that despite taking the square root, which kind of chops it into a smaller value, you still can make the entire term small, because square root n is still a large number, like 1,000. Right? So that means your n has to be 1 million to make the entire term very small. So that is, in practice, how we try to make this small. And t cannot be small, cannot be close to 0, because t is a little bit like bell curve, right? Except we change this to t, and t depends on the sample size. So there's this thing called degree of freedom, which is associated with how the t's tail end is being fattened or thinned out by the degree of freedom. So a large degree of freedom will make t looking like a normal bell curve itself. A small degree of freedom will make the tail fat and the top here lower than the normal bell curve. So I'm not going to discuss too much about all these differences between t and z, the standard normal distribution. But suffice it to say that for t to happen, t degree of freedom, right, looks like bell curve, normal distribution, and it is taking into account the lack of knowledge of sigma. Yes, the population standard deviation of the parent distribution. So the word parent allows me to emphasize that it is about X that we are talking about, this sigma, all right, this same sigma here. And imagine this, we are trying to find mu, means we basically don't know mu, right? That's why we want to find out or estimate mu. If you don't know mu, in practice, are you going to be able to know sigma? Because sigma is defined in terms of variance, sigma square. Sigma square is defined in terms of all the xi values minus mu. So it somehow implies that you should know mu first before you can know sigma. And if you don't know mu, the value mu, chances are very high that you also don't know sigma. And indeed, that's true in many of our real life scenarios. In other words, we normally don't have any idea, or even a close estimate of sigma unless we sample and calculate S. Then S will point estimate with very poor accuracy, especially when N is small. All right, so you see, S is a point estimate. Already there's loss of fidelity, right? Very loss of a good description, good numerical approximation of sigma. Some more, S itself, with low sample size, is going to be even worse estimate, right? Because with low sample size, the S value will swing ever more. It will be having a lesser, how to put it, lesser proximity, right? A high chance that it will deviate further away from sigma itself. So in other words, we have some sort of a double whammy. Not only that S itself, by construction, by birth, in theory, is just a point estimation, right? In theory, S is not equal to sigma. We know that. So, and yet, the way we obtain S through measurements is through a small n, usually. Right? Imagine getting 5, late stage cancer patients who are able to volunteer, sign the agreement to volunteer for the trial of average efficacy of a new cancer drug. All right, so the population mean, is the average efficacy. Is the efficacy high or low? That means, are we going to be able to sell the drug at high price or low price, right? Effective or not? And so the sample size cannot be a lot. Even if you have all the money in the world, it doesn't mean you can gather all the patients within the time frame given. Now, in the clinical trials, you can last for 1 year, 2 years, but even so, right? Even so, it doesn't mean you can get infinite patients, and even 100 patients might even be hard. So your N typically is very small, like 5. So double whammy here. S itself in theory is an approximation. N itself in practice is not large. So your lack of knowledge of sigma is to a very severe degree right now, right? We basically have no idea what's going on. That's why we cannot use Z in most situations. The normal distribution. Normal distribution requires us to have knowledge. So I'm just going to put in bracket here. Sometimes we have this form as well. And in most textbooks, you might see this, right? X bar plus minus Z sigma over square root. So to use Z means you must have knowledge of sigma. And typically in practice, we don't have. That's why I would just write one formula. So in practice, typically we'll just end up using this. And the T requires a number. You must feed a number in, then you get a T distribution. So what number is that? The DF here, as I said, the DF here is the degree of freedom and has a fixed formula of n minus 1. Okay, n minus 1. So, but it is linear in that. So the larger the n, the higher the degree of freedom. So when, and of course, T degree of freedom becomes Z, the normal bell curve, right, which is following normal distribution with a mean of 0, standard deviation of 1 as df approaches infinity. So if you have infinite sample size, then and you repeat that infinite sample size infinitely many times, then you form a distribution with infinite degrees. Basically, that's just another name for normal distribution with a mean of 0, standard deviation of 1. So that's just a brief background of what is T distribution, right? So it's invented, it's created, it's constructed by mathematicians, statisticians to look like bell curve, but fattening the tail a little bit to account for the fact that we don't know sigma's value very well. We know about a bit. We know we are estimating it with S, but S has got a lot of leaks, right? So not very accurate. So we cannot conclude with the same precision as if we knew about sigma, if we use sigma itself. So T is constructed to compensate those lack of knowledge. Take it that way, then you'll find it conceptually very easy to just think of T as a multiplier, that's all. Of course, if you Wikipedia, the T function, T density function description is complex, very, very complicated, right? Much more complicated than the normal distribution itself. But let's just leave it as that. So to construct a confidence, what did I write? Confidence interval, we just need this formula. That's all. Okay, let's just look at how we do that. So the first step is simply to take the measurements. So our first step, I'm assuming that we already made the measurements. We have already made the n measurements. So we have calculated x bar, s, n, and t, right? So t is the value we get from a given confidence level. So confidence level is in terms of confidence level, right, is a value technically between 0 to 100%, but in practice, we seldom go below 90%. So these are the typical values. That's it. If you want, you can put 99.5%, but these are the typical ones. If you try to be weird, creative, or funny, then you might want to write 99.99999%. Make sure you do mean the extra 9s that you put inside there, because one more digit of percentage here, one more extra decimal place, could imply you have to put in, your n will go up a lot higher. All right, I'm not necessarily saying it's exponentially increasing in sample size, but it's going to go up a lot higher. So make sure you can afford that luxury, right, of precision. Also, if you kind of do funny description or calculation the other way around, by having a confidence level of 10%, 50%, 60%, right, you're going to just make people frown. What are you trying to do? Right? Because you lack confidence. Confidence level is just like the level of confidence that you have. What's your estimated time of arrival, ETA? Oh, I'm going to arrive 3 p.m. plus minus 5 minutes. Usually we say that. But in practice, when we say that, when I earlier on said that, I say that in a more layman casual manner, right? That's what we say. 3 p.m. plus minus 5 minutes. But what is implied in this practical conversation is that I'm very, very sure, right or not? Yeah, I'm like almost 100% sure. Of course, Murphy's law always applies. So the moment I say, yes, I'm 100% sure, then the plane will be delayed. So I'm going to say, yeah, I'm pretty sure. But in practice, when we say pretty sure, or based on my personal credibility, I'm always trying to, not boast about, the confidence, right? So if I'm pretty sure, then I say I'm sure. So when we say we are sure, put in quantitative form, it might be 99%, 95%, 90%. One of these, that's good enough, right? So one of these, if you're super, super sure, then you want to be numerically very accurate, then 99% sure. But all these are indicating very sure. Right now, yeah, these are all indicating very sure. And we don't give a confidence interval with a low confidence level. In fact, lower than 90% is not already is not acceptable. 85%, 80%, people think you're trying to be funny, right? And it's not funny. So the typical values are these. Try to stick around with these. And in other words, if you are the producer, you are calculating the confidence interval to estimate mu. You don't have much of a choice. So stick with 95% typically, and people will not micro inspect your meaning, your intention, your ulterior motive for choosing 95% because everyone in the world chooses 95%, right? I mean, if you want to account for certain experimental adjustments because you're using, I'm just, giving example on the fly, you realize that you're using old second-hand purchased instruments whose accuracies you yourself doubt, so you give a 90% confidence interval. Okay, fine. You don't want to be too sure about the outcome. Fine. So that's your choice. But I'm just saying that you have a choice in confidence level, but you don't have too many choices. And this confidence level gives rise to T, right? So plus degree of freedom gives rise to the T value that we see here. Okay. Now, oftentimes we say T is both the distribution, the shape itself, and also the value. So it can be confusing. But within the context of discussion, it's quite clear. I mean, you cannot be multiplying a constant by a graph, right? So this has to be a number. What is this number? I'll show you in almost immediately right now. Just to have a line to say that this is the input. I want to create or calculate or construct a 95% confidence interval. So we pick. Now, so if you are the person constructing the confidence interval, you pick. If you are the student reacting to a quiz question, exercise question, then it has to be given to you. It's an input to you, right? From here, plus the sample size minus 1, yeah, because degree of freedom is sample size minus 1, gives rise to T. These two numbers, right? I don't mean addition. I just mean these two inputs put into the Excel formula or R or Python, you will get a T value, all right? I'll show you in a while where these numbers go. And this confidence level gives rise to T value. The sample measurements give rise to both X bar and sample standard deviation. And our choice of experiment N, like I said, has been determined upfront. We don't change halfway. So that's it. Everything is set. All right. So number one, we have the confidence level being set or determined, and that converts to the T value. Number two, right? What we do is we assert. So we look at our sampling distribution of sample mean, our X bar, and what is supposed to be the mu X bar, we're going to assert it as X bar. Okay, so what that implies is we are asserting. Asserting means do without proof. Assert mu X bar as to be equal to X bar. Now this is little X bar. It means a number, a real number, averaged out from the samples, right? Mu X bar is a population mean of the sampling distribution of sample mean. We're not interested in X bar. We're interested in X. Fortunately, theory tells us what we are interested in, the population mean of X, mu itself, is the same as mu X bar, right? And confidence interval calculation says you set mu X bar to X bar, the number that we physically can touch and average and calculate in Excel, R, and Python. Understand that difference now? All right, so we assert, right? So we set. So I'm going to put an arrow here because it's not the other way around. So we set x bar into mu x bar. This part is all theory and it's all exact and so correct. This part is what we set to do. We do without proof. Clearly, our sample mean cannot be the same as mu, correct or not? Yeah, we won't know. Even if it's accidentally the same number, we won't know. But we're going to think like as if we knew for sure. So if you ask me, you know what is population mean of x? Oh, it is x bar. But that's wrong unless you say plus minus an error interval. Okay, so that's what we're going to do. So we're going to say plus minus an error interval. So this is the error interval. All right, so we are going to, let's call this the lower limit and this the high limit. So those two values are, calculated from this formula alone, and then we are done. So what's the big deal here? The big deal here is that since we are asserting mu x bar to be x bar itself, we're going to be able to see that yeah, okay, like this. That the sampling distribution of sample mean is going to be centered around x bar. That's an assertion. We don't know that is true or not, right? That's an assertion. When actually, we're not supposed to see this. We have no idea about this, but I'm going to kind of review, ta-da, show it to you, right? So actually, mu is here. Right? Or mu could be here. Or mu could be here. Or mu could be here. I won't mess up the diagram. But just so you know, that mu can be somewhere along the x bar axis, but we don't know where. All right, we're just going to think that mu is equal to our x bar plus minus an error bound. It's like saying, when are you arriving? I'm arriving at 3 p.m. All right, because in the past, I've been arriving at 2 p.m. 55 minutes, 3 p.m. 05 minutes, 2 p.m. 58 minutes, 3 p.m. 2 minutes, and average out to 3 p.m., right? So in the past, that's the sample mean. Plus minus 5 minutes. So this time round, I arrive at exactly 3 p.m. 3 minutes. So that's not 3 p.m. But is that acceptable? It's within my error bound, right? So that is the sense of using this error bound, which is not too alien to us. So the confidence interval consists of these two numbers plus the confidence level. So 95%, 90%, right? So that's the construction of confidence interval. That's it. Very, very simple. Simple idea here. Okay, so that if mu is here and our x bar is somewhere else, so if you pick another sample, the x bar might be here, and so we have another bell curve which is like shifted away, and another bell curve and another bell curve. So that's the kind of situation we could end up with. Here's an example. So let's say x bar is 2.2. Standard deviation, sample standard deviation is 0.3. Our sample size is 16. And so degree of freedom is n minus 1. And that's 15. And so if you look up using Excel or R or Python, using the t dot inverse, right, or qt to find the inverse of what is it? inverse of t distribution with degree of freedom 50, you could find that the t value is 1.7531. So the confidence level, example, what we are saying is 90% confidence level. So where's the 90% on the diagram? Well, the 90% is here. Okay, so the larger the confidence level, they might differ by only a little bit, it seems, 5%, 4% here. But the 5% and 4% is going to eat up all the tail, right? Yeah, and it's going to extend the boundaries, the error bounds, by a large amount. So even though the percentage difference in the confidence level is not that big, it can turn out to be very big because of the multipliers here, the S value here. Okay, so this value is our confidence level. So if you say the confidence level is 90%, then this area, in other words, the probability here, right, under the PDF curve is going to be 90%. And I'd like to also highlight that it is also symmetrical. Therefore, the 5% of the tail is here, and the 5% of the tail is here. It will never be asymmetrical for confidence interval. Is that okay? All right, so that will always be a sort of a, because we don't know what's the value of mu, so we need to be unbiased. So it will be 5% left, 5% right. And it is good to also see the t-axis. And so we can also draw the t-axis, right, which shares the same curve. In fact, this curve is drawn using the t PDF, t distributions probability density. So the random variable, unfortunately, common usage is also little t, is the student t. Student little t, not capital T. So we'll just live with that because it's clear that now I'm using the little t to talk about the entire graph. And because we are asserting mu x bar to be x bar, so it seems now the x bar is going to be mapped to the 0 t value. So this is the so-called 0 standardized t value. We could map t to the x value. So it's like t is centered on the x bar value also. But the reason why we have this number, when you do the table lookup for t distribution, for example, this number is exactly t minus the, yes, right, t x bar minus t is going to be this t value here, 1.7, actually here. Well, not exactly, but going to be somewhere here. Occupying 90%, so 1.7531, and the corresponding negative 1.75. Okay, right. So obviously the axis, they don't they don't share the same scale. So 1 unit on the x bar is different from 1 unit on the t axis. But the idea is that when the t distribution goes from minus 1.7531, this value, minus t this value, minus this value, to plus this value, the area under the curve is 90%, centered at 0. The similar behavior exists in x bar in the sense that when you go from the low limit to the high limit, you cover 90% of the area. So that's the kind of distribution similarity between the two. So it's insightful, I guess, educational to see this link, but I'm not hinting that they have the same unit scale. Or plus one unit is different from plus one unit on X bar scale is different from plus one unit on the T scale. All right, but illustration wise, we can see this sharing of the same so-called bell curve, the T curve. Yeah. All right. With this, then we are ready to construct the confidence interval, being that it is X bar plus minus T of S over square root N. So that's 2.2, right? Plus minus 0.3 over square root 6T. And you can check that it is, so this gives rise to a confidence interval, a 90% confidence interval for mu, or mu of x. It's always for mu, because the confidence interval is a tool, is a range tool to target or estimate mu. So we never say 90% confidence interval for x bar, or little x bar, or capital X bar, or whatever. We're not interested in x bar. Please remember that. This capital X bar and everything on X bar is a platform for us to, it's like a telescope for us to look into the moon. The moon is our mu, our prized value that we are looking for, right? Is ranging from, if my calculation is correct, okay, 2.069 to 2.331, which is not bad. Okay, so that's just one example of the calculations involved. Okay, so far so good. Give you a moment to absorb this example. Now, we can try to, now that we know how to produce or construct a confidence interval, let's look at it from the reading side, the consumption side, right? If you are the one reading, right, looking or being presented with this confidence interval, what does it say? What does it mean to you? That's the interpretation part. All right, so what does it mean? To say that we have a 90% confidence interval is from this to this. What does it mean? What it means is, if you recall the sampling distribution of sample mean, we always come back to this because it's our tool, right? Our telescope to understand the universe of mu, of mu. So if we do one time, we're going to interpret the X bar and the S in this platform, knowing that mu, this red stick here, this position on the X bar axis, this dot here, is fixed. Of course, it better be a sitting duck, right? It better be sitting there and not moving. If the duck is moving around, flying around, we will have no chance, right? Because it'll be super difficult to locate or estimate mu. So mu is assumed to be fixed, a constant, and we can repeat our X bar again. Just do another n measurements, right? Take the average. So one way to think about it is, if I can rotate this, right? Rotate this. So mu here, or rather I center mu. So mu is going to be fixed in the middle. Okay, so this number could be, in fact, 2.0 exactly, but we don't know, right? We're not supposed to know. I'm just showing for illustration purposes. So we're not supposed to know this. All we do know is that in one instance, we recorded this. right? Sample size n, sample size n. And then another instance, we recorded this. Notice that I put this interval to be a bit wider because the sample standard deviation can be a bit larger, a bit smaller, depending on your luck, right? So then the next one could be shifted to the left, right? And you get the idea, right? In general, it is like that, right? So we can have this 4, 5, 6, 7, 8, 9, 10. You know I'm counting, right? Why? Because I'm trying to be having exactly 10 here. Why 10? Well, it's easier to describe the meaning that when someone tells us, I have a 90% confidence interval and the range is from this to this, obviously, number one, it is trying to tell us the population mean of whatever variable we are interested in lies somewhere between these two numbers. How sure are you? 90% sure. Is there a possibility of error? Yes, 10% possibility that it could be outside. So I'm way wrong, but unlikely because, I'm 90% sure. Notice that I keep saying 90% sure, 90% confident. I try not to say the word 90% chance or probability because when you have one sample measurement, when you do one such interval, one such bracket, your conclusion cannot be 90% sure. Your conclusion is either mu is inside or outside. You cannot say that there's the 90% chance that, right? One measurement doesn't give rise to a 90% chance that mu will be inside this interval from the frequentist definition of probabilities perspective, right? So if you look at probability as a repeat of past relative frequencies, something we'll discuss, then you will realize that one occurrence is either yes or no. Is mu inside or outside, correct or not? Because people can ask you this hard question. Is mu inside or outside? You cannot say, I'm not sure. It's a bit like the quantum physics kind of Schrodinger's cat. Is the cat dead or alive, right? If you don't open the box, you cannot say I'm 90% sure, right? It's either dead or alive. So we have a cat here, the mu here, right? Is it inside or outside? You can say, but you cannot say I have a 90% chance. So what is chance? What is probability? Probability, if you use again the frequentist definition of probability, relative frequency assumed to be having the same occurrences, same relative frequency ratios, everything again in the near future. Using that approach, then the only way to have a proper interpretation of the 90% is that if you repeat. So if repeated 10 times, right? If repeated 10 times, then 9 times out of 10, mu will be inside this. That is very, very appropriate interpretation of this 90% because we can count now, right? And that's why you notice that this one time, right, this one time here, I actually put it off center. That's intentional to show that, there is always this occurrence. But if you ask me which interval, if you repeat 10 times, which interval is not inside, doesn't contain mu, I cannot tell you. My answer will be, I don't know. I only know that 10% of my intervals do not contain mu. Because if you do know, then that will be a contradiction. You just take that out and you know that the rest will be containing mu, and you can just take the minimum, the maximum of all the low limits, the minimum of all the high limits, then you get a much better interval. And that sounds like a little bit contradicting the 90% confidence interval idea, isn't it? So we don't get free lunch. We don't get high quality knowledge without doing hard work. So the high quality knowledge is which interval doesn't contain mu? We don't know. Okay. Obviously, I draw only 10 because you get the idea. I want to show you the 90%. But we don't need to stop at 10. So essentially, we are trying to say that if repeated, right? If the 90% CI is repeatedly sampled. I need to just be accurate now. Basically, if repeated infinite number of times. So if it's repeatedly sampled and computed infinitely many times, then we can talk about percentage, right? Infinitely many times, then 90% of if the 90% is repeatedly sampled, sample size n. The sample size must be the same. Then 90% of those confidence intervals will contain mu, and which is the number we are after. So that is the sort of more appropriate way to interpret the 90%, because throughout the construction, we never utilize the notion of probability, right? So how come suddenly there's this meaning of probability? Okay, having said that, in practice, oftentimes we have only one such interval. Okay, could be this one, could be this one, could be this one. We don't know, right? We don't know that it's red. It doesn't contain mu. So if we get this one, we're still going to say that I'm 90% sure, as if, right? As if we are implying that I have a 90% chance of hitting mu to be from 2.29 to 2.53, for example, something like that. So it does feel like the sense of chance is involved, using another definition of probability, by gut feel. That I'm pretty sure. So the sureness gets, in a layman's sense, interpreted or explained as probability. But in exam, right, in more technical, in more official settings, the right way to understand or interpret the 90% is still to say this long bunch of words, right? Then it is more technically correct. Okay, next, we want to talk about the two kinds of problems. In fact, we have already covered one kind of problem. What kind of problem? Which is to forward construct the confidence interval, right? So given x bar as confidence level and sample size, construct the interval. So this is the first kind of problem. Second kind of problem is to second kind of problem is to calculate sample size or estimate sample size. So sample size becomes the output. Given the tolerance, right? And of course, mainly given the tolerance and confidence level. All right. So oftentimes we may want to know how much effort should we put in, how many households should we knock to determine whether the popularity of a particular election party is high or low within certain error bounds, correct or not? Yeah. So because we don't want it to be indicating that the party is kind of leading a lot, when actually in the actual polling results, the party fails. So we want to know, given a tolerance, what is the minimum sample size? Then maybe we can build from that. We add another 10%, we add another 50% just to be even surer, right? So that is driving the need for this kind of calculation. So recall again that we have this t over, so t times s over square root n, right, is our error bound, our tolerance. We don't need to worry so much about x bar anymore. Now, be careful here, however, is that t itself, the number t itself, can only be determined if we know the degree of freedom. So actually it's t of df. And t of df is actually n minus 1. But n is the number that we want to know. We're trying to determine n. So if we cannot determine n, how do we determine the degree of freedom? If we cannot determine degree of freedom, how do we calculate t? So there's no n to it, right? So this number is given, for example, 0.05 or 0.01, right? So this number is given. S can be estimated, leaving us with t and n. But t is a function of n, so we have a bit of a trouble. So typically, we don't use this, so we have to do a little bit of a trick and assert that z, all right, z times sigma over square root n is going to be our tolerance. Okay, because z value is very close to t value, and it is like as if it is t but having an infinite degree of freedom. Infinite degree of freedom, right? So if n, if the final n, right, is going to be larger than 30 or more, then essentially the values of z and t will be very close to each other. So close that they are like maybe the second, third decimal places, not much of a difference. So in practice, that just means we are not going to be too bothered by it, right? So end up it's not going to be too much of a problem. And this, however, allows us to continue because we can detach or divide out the z easily. So we just move this to the right as a numerator, divide this, and then put it into the denominator, right? So we end up having z sigma over tolerance is square root n. And then straight away, we get n is simply the square of z times sigma over tolerance. And typically we round up. So it's like taking the higher integer, even if we get a 0.1, 0.2, 0.3. More because if the exact number is to do 72.3 sample size, 72.3 measurements, then we better do 73 measurements, right? Just to be on the safe side, to be just within the error bound rather than just exceeding the error bound by a little bit. Yeah, so that's the idea. So essentially, with this formula, then we are done. We are able to use this formula to estimate the sample size. Okay. Quick example. That's my example color. Okay, so quick example. Let me shift myself. Okay. Shift. Oops, sorry, wrong side. Okay, shift myself to the right, to the left. Okay, so here we have an example. Okay, so a soft drink manufacturer wants to ensure that the caffeine in their drinks do not exceed certain limits. Okay, so you think about a busy manufacturing conveyor belt, right? Filling up all the cans of drinks, in a very manufacturing style, very rapidly. And what makes the management, what assures the management that the drinks are of uh, quality content? Quality meaning meeting the specification. Right? So what makes us think that it is quality? We cannot just say, "Oh, our brand is branded, so it is quality," right? So the quality of your brand doesn't come from you saying it. Quality of the brand comes from the discipline, right? The systems and the steps and the procedures that the management takes to ensure that the product meets the specification. Okay, so what does it mean? The meeting the specification means there is caffeine, but it should not exceed 100 milligrams per 100 ml of the drink. Okay, so this drink is 100 ml. Per 100 ml. Otherwise, right? Otherwise, it is a defect. It would be defective. So the drink, it will be discarded because it is defective. Okay, so that's it. Let's say the rest of the contents, right? The rest of the chemicals or whatever it is in the drink, they are all okay. Except we got to have an extra check on the caffeine because all of you know, uh, excessive dose could lead to very serious problems, right? So we have to be careful. And we can just give some numbers here since we're just giving an example. So we say that the population standard deviation sigma is estimated to be 2 milligrams. What is sigma? It's the population standard deviation of what? Of what? Of caffeine level per 100 ml. So in other words, in a lot of earlier measurements, earlier estimates, earlier sampling of 100 milliliters, sorry, it was measured carefully, right, that the fluctuation in caffeine level, which is the standard deviation, is estimated to be 2 milligrams population. That means we were pretty sure that it is quite stable. Okay, so then we ask what sample size is needed for 100 ml. Let me just put for confidence level of 99% to determine defective drinks. Okay. Now, of course, ideally, you want to check every single drink, right? So you want to um, take the output from the manufacturing machine, right? So very rapidly, very noisy and all that, but it comes out very rapidly. A lot of drinks being produced. Technically, you want to check every single can of it, but remember, it's a destructive test, right? You open up the can, then you cannot sell the can. So we are going to be contended with random sampling, right? So we want to be 99% sure, okay, And we want to be, sorry, I missed out one word. It would otherwise it would be defective. Okay. To be what sample size is needed to deter for confidence level of 99% to determine defective strings? Two. To within 0.1 milligrams level. Yes. This is the tolerance, right? Everyone can see that. So this is the tolerance. This is our sigma clearly, right? And we also have this. This is our confidence level. So we need three numbers, right? So we need the Z, we need the sigma, we need the tolerance, and we are done. So the confidence level is going to give rise to the Z value. Okay. And what is the Z value corresponding to 99%? Very simple. Well, we're going to just essentially sketch a Z, right, with a 0 inside there. Symmetrical, right? So 99%. 99% is always sitting in the middle. And 1% is to be split equally on the left and on the right. So this would have to be 0.5%, which means it is 0.005 in numerical value. Likewise here, 0.5%. Okay, so if you take the norm dot inverse in Excel, feeding it with 0.005, remember we convert the percent to a real number. So 0.005 without degree of freedom because we are not using t distribution, right? So in that case, you will get a value. So answer is at 99% confidence level, right? Our Z value is going to be found to be 2.5758. So this is the key, right? Plus minus, but we just take the positive number. If you do the norm dot inverse or Q norm in R of 0.005, you will get negative 2.575. But you can flip it around to get this number. So we want this number. So 2.5758 is what we want. And therefore, n is going to be 2.5758, yeah, times the sigma. What's the sigma? Sigma is mg. So this is mg per 100 liters, 100 milliliters. So everything is per 100, otherwise it will not be the right unit. So 2.5758 times 2, that's our sigma, then divided by the tolerance, 0.1. Okay, so just, that we don't need to adjust and for the change in units and all that stuff. So remember the squaring. And so this is going to be, if my calculation is correct, 2653.959. Now this case is clear. We're just going to set it to 2654 sample size. So this is the minimum sample size. Minimum sample size needed doesn't mean you have to go with exactly this number, right? Minimum means you cannot go lower, right? Because if you want to achieve this level of confidence level and this level of tolerance to be no more than 0.1 milligrams away from the truth, then you better have 2654 drinks being opened up and measured carefully also as to ensure this. It doesn't mean that you will have 99% of your produced drinks all okay. It doesn't mean that. we're measuring reality, or we are establishing a confidence, 99% confidence interval to estimate mu. Mu is the way nature is the way the manufacturer's defective product level is at this point in time. We're not going to change that. So it's not going to correct any problems. It's not going to make sure that you will have 99% of products produced being okay, right? So because we are just detecting, we're on the reading side of the reality. So once we destructively measure, because we are going to open up, randomly select 2654 cans, open them up, pour out the 100 ml, go through some chemical process to determine the caffeine level, and then make the measurement, right? If that entire process of constructing the confidence, now we do the other positive step. We measure X bar, S, and then form the confidence interval, right? If that is going to exceed the 100 ml, 100 mg per 100 ml, that means it's too much, right? Maybe it's 105 milligrams per 100 ml. So caffeine level being a very potent chemical, manufacturer needs to be very careful about that. So even a bit more is not acceptable, right? So 105 mg per 100 ml, the mean level is that, then basically the whole batch is to be destroyed. Because likely it indicates that even though, right, the 2,654 samples produce a confidence level, that is centered at 105 mg per 100 milliliters. And we're going to conclude that it indirectly means that the entire batch of produced, maybe millions of produced cans of soda drinks contain 105, maybe 107, right? We don't know. Or maybe 102. We don't know. But it's more than 100 milligrams. Then we are not going to accept the entire batch. Or because the action is on the population, it's on the entire batch for that day, let's say, right? Or for that factory. And if it is below, like for example, 99.5 mg per 100 ml, 99 milligrams per 100 ml, consumers will not sue the manufacturer for, hey, you bluff me, you say 100 mg, right? But you gave me 99 mg. Because, this is a very potent compound, right? And overdose is much more dangerous than underdose. Underdose is like, caffeine is supposed to boost your sports performance or your focus or whatnot. So 1 mg less is not going to be causing too much of a problem because it's just boosting a bit less, maybe undetectably. So you're not going to attract any problem, lawsuits, angry reactions or whatnot from the consumers. But exceeding, even if it didn't cause problem, but someone going to send it to the lab for analysis, the drinks manufacturer might just suffer from lawsuit in an unfavorable way, isn't it? Yeah, because you did exceed the 100 mg, and caffeine being a potent chemical compound is, this kind of existence is just not acceptable. If you have more vitamin C than the claimed 100 mg per 100 ml, that's fine, right? It's not so much problem. So when we look at 2654 and our conclusion is it is lesser than 100 mg, then we are more sure, right, that the population mean caffeine level per 100 ml is not exceeding 100 mg. So that's an assurance. And even if finally it was found to be otherwise, did the manufacturer do something scientific and systematic to ensure that the public's safety is taken care of by the manufacturer's product? Yes, we did do this sampling. You can look at my records, right? So the manufacturer can then be able to protect itself by having taken this step to verify its products. Of course, how to reduce? They must do something to the manufacturing side to tone down the injection of caffeine level. But as a check, are you sure you did tone down, right? Then this is the check, right? So now hopefully you can see why an instrument like confidence interval, which is just to estimate mu, um, which is just to estimate mu, ends up having a lot of usages because basically any number that we operate on. Operate on means we manage with the number, we plan with the number, we decide based on the number. That kind of number is not a one number. It is the average of many numbers. If you start thinking about that way, right, it is the beginning of the right way to think about statistics. And then you will realize that you are able to use all these in a more natural manner. All these tools, confidence interval, and the next one that we're going to talk about, hypothesis test, and various terms and theory from statistics, much more naturally, much more in line with why statistics is being developed the way it is. Okay. So thank you for your attention, and I see you in the next video.